Okay, so today we are going to walk through matter, properties, and change. And I'm going to be going through the honors presentation and going to link the honors presentation to both the college prep and honors. So if you are in college prep and you are choosing to watch the screencast of this lecture, then you can just move on and forget about the things that I discuss on the honor slides that do not show up on the college prep slides. So again, we're looking at matter, properties, and change, and we're specifically focusing today on pressure and its effects. So go ahead and answer these questions. Do you think that you would be able to draw up a liquid from the first floor to the 8th floor of a building using a straw? Why or why not? Maybe draw on some information that you gained from the straw video that you just watched and that you answered the questions on. Then the next question is, why is it that when someone wearing perfume, lotion, or cologne, you are able to smell it even if they are not sitting right next to you? So an example that I usually use in class is, say we're sitting in class and say you have Cam is in the front of the class and Cam lets one rip, and all of a sudden eventually you're going to end up having Edgar is going to smell it all the way in the back side right corner or something. Eventually Edgar smells that, and why does he smell that? And the reason, looking at that, what do you think the reason is? What's happening on a particle level? What's happening to those? So go ahead and type in your answer and move on. So before we move on, though, I would like to go back over something that we did talk about last week, and that was properties of gases. So we went through solids, liquids, and gases and how close they are or how far they are apart from each other. And gas has these properties due to the distances between the particles of the gas. So because they have much greater distances than solids and liquids, gases are going to be more fluid. Remember, the word fluid does not necessarily mean we're talking about a liquid. We're talking about flowing, easily moving past each other. So gases are fluid. They have a low density, and that's because density equals mass divided by volume. And if you're dividing by a very large volume, that's going to give you a very small density. Gases are highly compressible, and this is because there's a lot of space between them, and gases will completely fill the container that they are in, whatever that container is. So pressure, what is pressure? Pressure is the force per unit area. And there is actually a really good video on your first CK12 link. If you're still confused about pressure after this, you can look at that. It's a Bozeman video, and there are other videos that you can find online, or you can reach out to me. But where does that pressure come from? So think about gas particles. Gas particles are moving around fast. And they're moving and they start colliding with each other and colliding with the sides of the container. Every single time you have that collision with the side of the container is going to register a pressure, a force per unit area that is collided with. We measure pressure with a barometer. So pressure, when we're measuring pressure, a lot of pressure questions or questions that involve pressure are going to say something like STP, or standard temperature and pressure. It is important for you to know that STP, or standard temperature and pressure, is either 0 degrees Celsius or 273 Kelvin, which is the same exact thing. And the pressure of that gas is at 1 atm, 1 atmosphere, or 101.3 kilopascals, because kilopascals is what our SI unit is. But any gas or anything that is at standard temperature and pressure, or STP, you know the conditions of temperature are 273 Kelvin and pressure is 101.3 kilopascals. We'll reference STP a lot this year, so it is very important for you to know that value. So you're going to go ahead and watch this video and see how barometers were first invented. And then you're going to go ahead and come over here and answer this question. So explain how Torricelli's barometer works based on the video that you just watched. So use some information from the video to answer this question. Old-fashioned water pumps. So if you have an old house that you visited or anything and you've ever seen a water pump and maybe even you've made it work, you push the lever up, and by pushing that lever up, what you're doing is you're removing the air from the column by pulling up on the lever. So you're removing the air, and then what happens is that pressure is really reduced in that column, but the outside pressure, the pressure that's on the water outside, is the same, but it balances that. So because it's the same as it was, but it's more than what it is inside that column now, what happens is the air around it allows for that water to be pushed up into the spout, into that column or into that pipe. And then, so when you push it down, then the water is going to end up coming out. Now, you can only get water naturally to a maximum height of 10 meters without a pump. And that's because of atmospheric pressure. Because what your atmospheric pressure is, it's not going to push beyond that. So Dalton's law of partial pressure. One thing that I think makes a lot of sense, but maybe it's just because of the way I look at it, but if you have, gas A, and that gas A exerts a pressure of 5 atm, and then you add gas B into the same container, and gas B had a pressure of 2 atm. The sum of those pressures, each of those is a partial pressure, and the sum of those pressures adds to 7 atm. So your total pressure, this is Dalton's law of partial pressures. Dalton came up with this law that the total pressure is equivalent to the sum of all of the other pressures. Now, it also depends on the amount of gas that's present, but we're not going to talk about that as much, just understanding that the pressure of 1, or A in this example, plus the pressure of B adds up to the total pressure. So the kinetic molecular theory, this is the main point in today's lesson. Obviously, you need to know what pressure is, but then you also need to understand how gases behave. Now, mind you, gases, this is going to be an ideal situation. So we have ideal gases and we have real gases. Real gases have attractive forces and they don't follow the kinetic molecular theory. But ideal gases, in a hypothetical perfect world where there are no attractive forces, gases are going to behave this way. And it's because gases are moving constantly. So gases are far apart relative to their size. And think about it this way. When it is like 100 degrees outside, you don't want someone sitting right on top of you, right? Like that's super uncomfortable and awkward. So if you think about it, those gas particles are moving and they're moving and they're moving, they're moving, and they want to be far apart from each other because it's one of those like, it's too hot, get off of me, I have too much energy, get away from me. So the gas particles, for all of these particles that are moving around, they are really far apart relative to their size. Mind you, they're really, really tiny particles. Collisions between these gas particles are perfectly elastic. Now, this is going to play in as being very important if you were to go on and take physics. But the biggest thing is these perfectly elastic collisions means that there's no net loss of kinetic energy. Something that we do study in physics is that you can tell something is an elastic collision versus an inelastic collision if your kinetic energy is conserved. So in this case, your collisions are perfectly elastic, which means there's no net loss of energy. Gas particles are in constant, rapid, and random motion. They're moving and they're grooving and they just want to keep going. They don't want anyone to mess with them. They just want to keep going. So gas particles are far apart relative to their size. Their collisions are perfectly elastic. They're in constant, rapid, and random motion, and there are no attractive forces between them. They want to be as far apart from each other as possible. They're not attracted to each other, so they're not pulling into each other. So there are no forces of attraction. And then also the temperature of a gas is dependent on the average kinetic energy. So go ahead and watch this video and answer these two questions. Why does it hurt so bad when you jump from a diving board into a pool of water? I really like the example used in this video. And then also using the kinetic molecular theory, explain how the particles move differently between a solid, a liquid, and a gas. Okay, so you're going to go ahead and answer those here. And then you're going to go ahead and watch this video. So this video is kind of interesting about how smell can be launched and just how smell is going to move through the air. And it goes a little bit deeper than anything that we really need to do for this class, but I thought that it was an interesting video. So you're going to answer that question. How does smell travel through the air? And then the last thing that you're going to do for today is you're going to look at this PhET simulation. So the PhET simulation is going to allow you to explore. So you can explore by, say you wanted to go to this tab and you click over here on the particles and say I want a whole bunch of light particles. So I'm going to add a whole bunch of light particles. The more I add, more particles I have. And then what if I want to cool that down? What happens to the particles and what happens to the pressure? What if I want to take this and I want to change the volume? Okay, what happens to the pressure? What if I get rid of some of the gas and let some of the gas go? Okay, how does that affect things? So, how do all of these different parameters affect the pressure and affect gases? Basically, you can look at the collision counter, so it'll tell you how many collisions there are when you hit play. Okay, and then you can move on. You can look at the energy involved in the situation. So here you're going to end up seeing the number of particles and the speed. You can click here to be able to see the kinetic energy. And then you can also look at diffusion and what are the effects of diffusion if I change different parameters here. So if I change the number of particles, if I change the mass of the particles. So go ahead and mess around with this. You also have ideal gases here, and you can change your particles here. You can choose to hold things constant, hold nothing constant, whatever you want to do here, but allow yourself to mess around with this. Take probably about like 10 minutes and tell me, how does the temperature affect the motion of the motion or the pressure exerted by the gases? And what can you change to affect the volume? Do you notice anything interesting about this experiment? And then you're going to move on to your very last question. This is going to be your check-in question for today. And your check-in question is going to be, what did you like about this lesson? What did you not like? Was it easy, or what was easy and what was hard? You can go ahead and draw, you can go ahead and answer, and then you're done for today. So I hope that was helpful for you. Thanks for joining me.